Okay. Thank you.
Actually, you are supposed to submit your assignment today, I think. All right, let's see. All right, guys, let's continue. If you remember, we were talking about spanning sets and linear independence, two concepts. And we did a few examples. Let's have a look quickly what we did the last time. So example 1, and actually we learned that the connection between the system of linear equations, right, and spanning sets or linear combination of the vectors and okay, linear dependent and linearly independent vectors. And we did these examples. Okay, so we stopped here, and also even we actually started this theorem. Let's just continue from here. So this theorem says that vectors, it should be vectors v1, v2, vm. Okay, and what are these vectors? These are vectors from what is it, n-dimensional space. They are if and only if at least one of the vectors can be expressed as a linear combination of the others. Okay, so linearly dependent, it means that if you're given a set and if the vectors are linearly dependent, and there's a case that always we can express at least one vector as a linear combination of the remaining vectors. What does it mean? We know that since these vectors are linearly independent, right, as you know from the definition, we can find as scalars, we have such scalars, let's say the C1 and C2 dot 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 Cm, not all 0, right? That means at least one of them is not equal to 0. So that the linear combination of these vectors C, M, V, M is equal to 0. And here, since we are saying that at least one of them is not equal to 0, one of these coefficients, right, either C1 or C2. Now suppose that let's say Cm is not equal to 0. I'm sure that it's not equal to 0. Okay, and other, I don't know, they may be equal to 0 because our condition is at least one of them is not equal to 0. Not all 0 means at least one of these coefficients is not equal to 0. Then I can just write these vectors as, I mean, taking everything to the right hand side and keeping this vector on the left. We will have this equation, Cm Vm is equal to minus C1 V1 minus C2 V2 minus dot 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 Cm minus 1 Vm minus 1. Now, since Cm is not equal to 0, I can divide both sides by non-zero number. If you divide both sides by Cm, then we will have here Cm is equal to minus C1 over Cm. Here we have the first vector, minus C2 over Cm. Here we have the second vector, dot dot. Here we have Cm minus 1 over Cm times Vm minus 1, the last vector. That means that now I can just relabel this. I can just relabel this maybe as A1, and this one is A2, and this one A3, whatever it is, M minus 1. So that means that we have expressed this vector, right, one vector from this set as a linear combination of the other vectors in the set. Okay, that's the case. That's always possible. That's always the case. At least one of the vectors. I'm not saying that any one of the vector, at least one vector. All right, any set of vectors containing the 0 vector is linearly dependent. If you're given a set, if the set contains 0, immediately we can say that these vectors are linearly dependent. Why is it so? And also last time we have already proved this. I'll skip this one. And we have another example here. Determine whether the following sets of vectors are linearly dependent. Okay, here we have 4 examples. I mean, we don't have to do all of them. I'll just show one example from here. Whether the following sets of vectors are linearly dependent. Let's do D from here. Okay. To do this one, that means that if this vector is, let's say, U, this vector is V, this vector is W, can we just find three numbers here, C1, C2, 3, right? At least one of them is not equal to 0, so that C1 times vector U plus C2 times vector V plus C3 times vector W is equal to 0. If we can find such non-zero tuple here, the three numbers, that means that these three vectors are, what is it, linearly dependent. Otherwise, if the only solution of this system or this equation is trivial means all the solutions are 0, then these vectors are linearly independent. It's no way that we can express any vector here as a linear combination of the other vectors. Okay, and as you know, what is the geometric representation of this one? That means that all of these three vectors, they are not any of these two, they are not, what is it, parallel to each other. Okay, so as you know that we know how to solve this system. To solve this system, as you see here, if I just put here, substitute here, right, we will get this augmented matrix. The first column will be the first vector, that is 1, 2, 0. The second one will be 1, 1, negative 1. And third one will be 1, 4, 2. That is homogeneous system. Here we have 0, 0. 0 is always 0. That's why I can just actually ignore writing the last column. I just assume that here we have one more column, that is the 0 column, constant terms column, right? So now if you just bring this or reduce this to reduced row echelon form, multiply the first row by negative 2 immediately and add to the second row. Here we have 0, negative 2 plus 1, that is negative 1, negative 2 plus 4, that's equal to 2. And here we have 0, negative 1, 2. And as you see here, the second and third lines are exactly the same. So 1, 1, here we have 0. Let me just negative 1, 2. Here we have 0, 0, 0. Right. Now I can just add the second row to the first one. Then we will have here we have 1, 0, 0, negative 1 plus 1. 0, 2 plus 1, it is 3. And multiply the second row by negative 1. Here we have 1, negative 2, 0, 0. Okay, now if you just write the equation of the system here we have C1, that is C1 plus, that is a coefficient of C3, 3C3 is equal to 0. And the second one is C2 minus 2C3 is equal to 0. As you see here, the rank of this matrix is 2. That means that we have at least one free variable. What is the free variable? That is C sub 3. So from here, let's say C sub 3 is equal to T, and we will get here what is C sub 2. And take to the right hand side, we have 2 times C sub 3, that's equal to 2T. And substitute here, C sub 1 will be, what is it, minus 3T. So what is T here? T is any real number, it's a scalar. That means that if T equals 1, we get one solution. If T equals 2, we have one solution, right? So that means that in infinitely many ways, I can write these three vectors. I mean, the linear combinations of these three vectors will give us 0 vector. This one is not 0 scale, it's 0 vector. So that means that these three vectors are, what is it, linearly independent. Somebody, can you mute your microphone? I can hear something from there. All right. Theorem 2.6. Now we can actually summarize what we have done earlier. Now we will see something that's a kind of rule, right, that applies to all these cases. It says that let V1, V2, Vm. Here we are given m vectors, be column vectors in Rm. What does it mean? It means that we are taking m vectors. Here we have, what is it, n dimensional space. That means that each vector has n components. So we are taking this vector from this space. And here we have Vm, right? And let A be the n by m matrix. V1, V2, Vm, with these vectors as its columns. Okay, we have another matrix, and columns are these vectors. So then it says that V1, V2, Vm are linearly independent if and only if So if and only if one more time, that means that here we have this kind of implication, both direction, right? If the homogeneous linear system with augmented matrix, this one has a non-trivial solution. Okay. So that means that, guys, to make this clear for you, what we're trying to say here is when you're proving this thing, you just take one particular case if you cannot actually imagine the whole thing. So assume that here we are talking about three vectors, v1, v2, v3. And these vectors are from, let's say, n dimensional space. Okay. So now it's saying that then v1, v2, v3 are linearly dependent. Now assume that in this actually implication, okay, this way, assume that the first statement is true. So this if and only if means here we are given two statements, and if and only if, and here we have B. What does it mean? If it means that if statement A is true, also B must be true. Or if statement B is true, then A must be true. That if and only if means this. So now I assume that I suppose that this A statement is true. That means that we mean this V1, V2, V3 are linearly dependent vectors. And by the previous theorem, what did we actually say here? We say that if vectors are linearly dependent, if and only if at least one of the vectors can be expressed as a linear combination of the others. Here, assume that one of the vectors, that vector is V3. Assume that V3 can be expressed as a linear combination of V1 and V2. That is, here we have C1, here we have V1, plus C2, and here we have V2. Okay, from the previous theorem. So that means that now we have to show that this homogeneous linear system with augmented matrix, this, right, has a non-trivial solution. So that means that now we have to show that the system, which is, what is matrix A? The matrix whose columns are these vectors. Here we have V1, actually here V2, and V3. And here we have actually 0, right? Okay, column vectors, linear dependent. Okay. Okay, good. Homogeneous system. Should we use this? Okay, just then V1, V2, Vm are linearly dependent if and only if the homogeneous linear system with augmented mass has no trivial solution. Okay, these are linearly dependent. All right, all right. So I think I need to make different approach. It's also fine, but other way is much better. Okay, so these vectors are linearly dependent means I can find such this C1 and C2, C3, right? These are scalars, not all 0, at least one of them 0. So that C1 times V1 plus C2 times V2, these are vectors, plus C3 times V3 is equal to 0 vector. Right? And at least one of them is not equal to 0. Right? Now from here, what is this? It's just what is the augmented matrix of this system. It is just this thing, that is A, and whose columns are V1, V2, V3, and here we have 0 because on the right hand side we have 0, right? And this augmented homogeneous linear system with augmented matrix, this one, right, has a non-trivial solution. Why? Because this C1 and C2, C3, these are the solutions of this system. And at the beginning, we say that not all zero. That means that at least one of these numbers, the coefficients C1, C2, C3, that's not equal to 0. That means that this vector is non-trivial. This C1, C2, C3, that is the solution of the system that is not equal to 0, because at least one of them is not equal to 0. Okay. And how about converse? Conversely, if we assume that if the homogeneous linear system with augmented matrix has a non-trivial solution, then we have to show that these vectors are linearly dependent. So it has non-trivial solution means I can just write it as C1 V1 plus C2 V2 plus C3 V3, and we are saying that it's non-trivial. That means that at least one of them is not equal to 0, and the linear combination of these vectors is equal to 0. That means that these vectors V1, V2, V3, they are linearly dependent. Okay, that's what this theorem says here. Example 8, the standard unit vectors, right? In Rn, they are linearly independent, right? Why is it so? Because if actually, for example, let's say again, if you just take this E1, E2, E3, let's say they are from three-dimensional space. What is E1? E1 is this vector that is 1, 0, 0, right? E2 is this vector that is 0, 1, 0, and E3 is this vector 0, 0, 1. Right? So now how do we know that actually these are linear independence? And because here, if you just write this C1, right, E1 plus C2, E2 plus C3, E3, and if you just multiply the first vector by C1, here we will have C1, the second one by C2, here we will have C2, and the third one, the third component is equal to C3. And here we have C1 and C2, C3. And this vector is equal to 0 vector when if all of them are equal to 0 at the same time. It's the only solution. And this implies that C1, C2, and C3, they all must be equal to 0. So that means that the solution of this system is trivial, which means that these vectors are linearly independent. In general, all the standard unit vectors from Rn, even if you take n or any number of these standard unit vectors, they are linearly independent. All right, another example, determine whether the given row vectors are linearly dependent or not. Okay, now here, intentionally, we put this question here because we are now going to get some kind of general rule, and we will see actually this as a theorem in the next page. Okay, before we move to the theorem, let's actually solve this question, and you have some idea that really helps you to understand the theorem. Here, determine whether the given row vectors are linearly dependent or not. Okay, so far, if they are column vectors, we know what to do, right? If you if these vectors are column vectors, we have to reduce them to reduced row echelon form, and after that we will see, right? Do we have any 0 row or not? But here we construct a matrix with these vectors as its rows and proceed to reduce it to echelon form. Each time a row changes, we denote the new row by adding a prime symbol. And as you see that actually these operations will produce a chain of linearly dependence operations. That is, for example, let's say if we just form our matrix, here we have the first row like U, V, W, and these are row vectors, and the components of U, that is 1, 2, 0. These are not column vectors, don't get confused here. V, the components of V, 1, 1, negative 1, and here we have 1, 4, 2. Right? So that is the first row and the second row and third row. Okay. So now let's reduce this to reduced row echelon form. The first, actually, I need to create zeros under this one, right? So this new row, I will denote this by R2 prime. So what is R2 prime? R2 prime is equal to, what is it? R2 minus R1, right? So as you see here, if I subtract R1 from R2 and write it in the second row, what do we get here? 1 minus 1. Let me just write the first row first. 1, 2, 0. 1 minus 1 is 0. 1 minus 2, negative 1. Negative 1 minus 0 is equal to negative 1. Now the same thing for R3. Let me just denote this with R3 prime. That's equal to, that is R3 minus R1. This R1 didn't change yet. That's why I'm not using any prime notation here. 1 minus 1, that's equal to 0. 4 minus 2, that's equal to 2. 2 minus 2, that's equal to 2. Now, if I multiply the second row by 2 and add it to the third row, we will get zeros here. So now actually here we will have new row here, right? So that is R3 double prime now because it's new row here. How do I get this? New R3, that is R3 prime, right? This one is R3 prime. That is plus 2 times this R2. That is a new one. So I should multiply this thing, right? Here we have R2 prime. If you do so, what we have here? Here we have 1, 2, 0, 0, negative 1, negative 1. And 2 plus negative 2, that's equal to 0. 2 plus negative 2. So here we have 0, 0, 0. Right? And immediately we can see that these two vectors, they are linearly independent. The scalar multiple of 1 doesn't give us the second vector. So actually we can see that they are linearly independent. I can stop here. So what we have done here is we actually created a 0 row in this, right? So now if I just substitute here, it's very interesting. So here we have R3, right? Actually, as you see here, R3 double prime. What is it? R3 double prime, that's equal to 0. I can just start with 0 vector. Let me here we have 0 vector, okay, equals, that is R3 double prime. And what is R3 double prime? Is equal to this. So if you substitute here, here we have R3 prime plus 2 times R2 prime. Continue. Now what is R3 prime? As you see here, R3 prime equals R3 minus R1. So that's equal to R3 minus R1 plus 2 times, what is R2 prime? That's equal to R2 minus R1. And if you simplify this, here we have R3 and minus R1 minus, actually here we have plus 2R2 minus R1 plus 2 times minus R1, that is minus 3R1. Now if I just substitute here, what we got here? This R1 is the first vector, that is our vector U. R2, that is the second row, that is vector V. And R3, the third row, that is vector W. So what on the left hand side, we have 0 vector. Now I can just write it as minus 3 R1, that is vector U, plus 2 times R2, that is vector V, plus R3, that is vector W, is equal to 0 vector. And on the left hand side, what we have here the linear combination of these 3 vectors. On the right hand side, we have 0, right? So thus, the rows of a matrix will be linearly dependent if elementary row operations can be used to create a 0 row. All right. So actually, if you're given row vectors, by actually applying or using a bunch of elementary row operations, if you can create 0 row here, that means that these vectors are linearly dependent. If it is not the case, that means that these vectors are linearly independent. That is one method to, how to say, determine if the given or a set of vectors are linearly dependent or independent. So now we can summarize this. Actually, this is a kind of finding as the following theorem. So let V1, V2, Vm be row vectors in Rn. Again, actually, we are taking this vector from our n-dimensional space. So these are this V1 and V2, V3, and we have a lot of vectors here. And this n-dimensional space, as you know, that each vector is or consists of n components, right? So vectors are n. and let A be the m by n matrix of these vectors as it is rows. Then V1, V2, Vm are linearly dependent. Okay, we have 10 minutes left. If and only if rank of A is less than m. Okay. So how do you prove that? Again, here, as you see, we are using if and only if. That means that if these vectors are, what is this? Okay, then these vectors are linearly dependent, then rank of A must be less than m. Or if the rank of matrix A is less than m, then these vectors must be linearly dependent. Okay, so now again, just to explain this, that after that, instead of 3, we can write m. Okay, assume that we are given 3 vectors, v1, v2, v3. Okay, and let's say they are from n-dimensional space. Actually, here it doesn't matter. All right, so now we are saying that they are linearly dependent. Okay, now we are proving in this. Okay, now I'm assuming that they are linearly independent. Now I have to show that rank of A is less than m. So linearly independent, as you know, that means that at least one of these vectors can be expressed as a linear combination of the others. As you note here, this V3, I can express it as a linear combination of V1 and V2, right? So now if we just write these vectors here, we have V1, V2, V3. What is V3? That's equal to C1 V1 plus C2 V2, right? So now if I multiply the first row by negative C1 and add here, that means that here first R3, okay, is equal to R3, let's say R3 prime, minus C1 times R1. What do we have here? Here we will have V1, V2, and minus C1 times V1 plus C1 plus, that's gone. Here we have C2, V2. But now again, new R3 double prime. Here, I can just actually multiply the second row by minus C2 and add it to the third row. So here we will have R3 prime minus C2 times R2. Now what do we have here? Here we will have V1, V2, 0. Now how many rows we have here? 3 rows, right? And how many, what is it? Columns n, whatever it is. So here, as you see here, we have 3. What is the rank? Actually, the rank of matrix A. Let's say this one is matrix A. It has originally 3 rows, right? As you see here, we have at least 1 row. So it cannot be equal to 3. It must be less than 3. Because here I took 3 vectors. If you take m vectors, at the time I should write here m vectors. That is what we are trying to say here. Okay, and also converse will be true, and you should just actually go from the last step towards the first step. Okay, and you will get that if the rank of A is less than m, we will see that these vectors are linearly dependent. Okay, that's the one slide, then I will finish the class. You'll have some break. Any set of m vectors in Rn is linearly dependent if m is greater than n. What does it mean? It means that any set of m vectors, we are given m vectors in Rn, is linearly dependent if m is greater than n. That means that here, for example, one example, let's say we are given 3 vectors. You give me 3 vectors, v1, v2, and v3. Okay, let's say they are from 2-dimensional space. So here our n is 2, m is 3. We just pick 3 vectors here. And we are saying that this set, which contains these vectors, v1, v2, v3, they are always linearly, what is it, dependent. Why is it so? Because here the number of vectors is greater than the dimension of these vectors, right? So the same thing happens. How about if I take 4 vectors, let's say v1, v2, v3, and v4, but all of these vectors are from maybe 2-dimensional space or 3-dimensional space. So now if you form a set using these vectors, And all of these vectors are, what is it, linearly dependent. Okay. Discipline is a bridge between goals and accomplishments. Guys, before we have our break, if you are there, if you are listening, maybe others, they can watch this, I don't know, they can, as you see, how many weeks we have already finished? About 2 weeks, and maybe today or tomorrow, not today, maybe tomorrow, I'm going to finish chapter 2. So you are going to have 2 quizzes soon, okay? It may be any time, but you should get ready for the quiz. It may be this Friday or next Monday or Tuesday. You will have 2 quizzes, quiz 1 from chapter 1, quiz 2 from chapter 2. And after that, maybe September 14 or 15, you will have midterm from the previous chapters. I don't know how much we can actually learn, all right? The midterm covers all the previous chapters that we studied from the beginning of this summer school time. Okay, and also you need to submit your assignment. I think today I will put your assignment scores into the system, and I hope you are preparing for your projects. All right, if you are late, if you do not submit before October 5, and it will be 0, and also you should know that. Okay, see you after 10 minutes. If you have any questions, you may ask now. If you have no questions, I'm going to close after 1 minute. Okay, see you after 15 minutes.